To think a little more deeply about this idea of average velocity versus instantaneous velocity, let's consider a position versus time graph for the person moving. So they started at -1 meter. So there they are. And they end up at 2 meters, and there's my origin. Okay, so let's consider these two states. I know that this is my initial position, and it occurs at 0 seconds. And I know that this is my final position, and it occurs at 10 seconds. So I can say on my position versus time graph, the position is always on the y-axis. So you can imagine like rotating this here. So they're starting out at -1 meter. That is right here. And they are at a time, which is on my x-axis here, of 0 seconds. So this dot corresponds with them right there. Okay? And I know that this dot corresponds with their final position, right? Because they're at a position of 2 meters on the x-axis at a time of 10 seconds. Okay, so let's imagine, to start with, that they just walk at the same speed the entire time from point 1 to point 2 here. Their position versus time graph would look like this, right? They would just be moving at 0.3 of a meter every single second for 10 full seconds, so that they cover 3 meters. If I wanted to find the slope of this graph, I could simply take my rise, my change in y, right? Or in this case, my change in r vector, which is 3 meters, my change in time, which is 10 seconds. I know that my slope is going to be my change in r, right? My height divided by my change in t, which is velocity. So here, the slope of my position versus time graph is my velocity, because it represents the division of how far did I go divided by how long did it take me to go that far. So here you'll find that the slope of this line is 3 divided by 10. And this line here represents a constant velocity. Because, for one, the slope never changes. If my slope is velocity and the slope doesn't change, that means that my velocity doesn't change, right? So this is the simplest case, but imagine that instead the person did some other path, that instead of going straight from point 1 to point 2 at a nice stable speed, they instead ran in the negative direction and then ran back. So this corresponds to the person running. They probably made it to, say, -3. So they ran over here and then they ran back. This plots out their position over time, but it is certainly not a constant velocity. How do I know? Well, they started out moving to the left and then they ended up moving to the right, and those two things are just different, right? It is completely different to be moving to the left as a velocity than to be moving to the right. So what we'd like to be able to do is be able to find out a little bit about the velocity of this person at any given moment if I know their position for the entire time. So instead of just closing my eyes and then opening them again when they're after 10 seconds, I watch the person the entire time and they plot out this graph. I just say, okay, they're here and then they're here. I take data for every given moment. I plot out exactly their position. And I want to use that in order to find out their velocity at any given moment, not just their average velocity, but their velocity at any given moment. Well, I can still use the fact that the slope of the line is equal to the person's velocity. Okay? It was true when it was a constant velocity, and it is true at any other velocity. Even if the velocity is changing, I can still take the slope of my position versus time graph as that person's velocity. So, for example, I could pick this point, and I could try to find the slope of the line at that point. Graphically, how I do this is I just try to draw a line which touches my curve at only that point. I didn't do a great job of it, but we're close, right? I want to draw a line that only touches my position versus time graph at that exact point. And if I can find the slope of this blue line, I know the slope of my red line at that point. Okay? So I could try to estimate it, right? I could say, okay, well, if I want to try to find the slope of the blue line, I go from about -3 meters to about so this could be like -3 meters, and this could be -1.2 meters. So I know my change in position over that amount of time, and I know that this is 2 seconds. So I could estimate the slope of this line from my various things here. Delta R looks like R final minus R initial, which is -1.2 meters minus -3 meters, and both of these are I hats, which is going to be 1.8 meters. All I have done is I have taken the rise here that I just kind of estimated by drawing this line. And now I can say delta t is 2 seconds. So my velocity here is approximately, because I'm not being very specific about this, 1.8 meters divided by 2 seconds, whatever that comes out to be, 0.9 meters per second. I hat. Okay, so my slope at this moment right here is about 0.9 meters per second in the positive x direction, which is bigger than 3/10 here, right? Notice that my slope is steeper. That means that my velocity is higher at this moment, right? So I have a higher velocity at this moment. Likewise, I could try to do this at another point. I could do it right here. So I'll erase a little bit of this. Do this point here. Can draw a line that touches only at that point. This one's actually really easy because my delta R along this line is 0, right? I can move as far as I want along this green line and never change my position. Not changing. My delta t, well, I don't know. I don't really care. Let's take a little 2-second window here. So my velocity looks like 0 over 2 looks like 0. So right here, my velocity is in fact 0 because the slope of my position versus time graph is 0 at that moment. Okay? At any given moment, you can take this slope and find the velocity of your curve. Notice that along this slope, the velocity is almost never equal to the average velocity that I would find just by doing delta r over delta t. My slope is very different along this than my average velocity. To actually use this equation, we would need to know something about the position as a function of time. So for example, if I had my position as a function of time is 4t squared I hat, right? Well, then I know that dr dt looks like 8t I hat, and that would be my velocity at any given moment. If I actually plotted this, well, at t equals 0, my position is at 0, and then I look like a quadratic function, so I'm going to go something like this, right? I am moving in the positive x direction, and I'm moving faster and faster in the positive x direction, and you can tell because my slope, initially my slope is very low, and then my slope becomes steeper and steeper, indicating that I am moving faster and faster in the x direction, okay? Which brings me to our next subject, which is acceleration. Acceleration is your change in velocity divided by the change in time. It is very important that you clearly distinguish in your mind between velocity, which is how fast your position is changing, and acceleration, which is how fast your velocity is changing. You can guess that this equation is going to hold if I had the same thing for the velocity is the change in position over the change in time, and that's dx dt or dr dt, then my acceleration should be dv dt. How fast is my velocity changing? If you think about it in terms of a car driving on the highway. So I have a car driving down the highway. If I am driving at 50 meters per second down the highway, at that constant speed, well, my acceleration, dv dt, or I could write it for constant velocities, I could write it as just deltas, right? As opposed to having to take some continuous calculus limit, I can say, well, if my speed is constant, then my change in velocity is 0 over some amount of time. I don't care what that time is, 0. So if you are traveling at the same speed or at the same velocity down the highway, you are not accelerating, right? When are you accelerating when you're in your car? Well, if you're at a stoplight and you are just speeding up, then you're accelerating. Your velocity is changing. If you see a stoplight and you hit the brakes and you're slowing down, then your velocity is changing. In those situations, you have a change in velocity, which means that you are accelerating. Interestingly, even if you're going around a corner, your velocity is changing. And that's because your velocity is a vector, it points in some direction. So say my marker, my velocity vector points to the right, right? So I'm moving this way, and now I turn, which means that my velocity vector has changed. Even if my speed didn't change, my direction did, which means that I was accelerating. So you can accelerate either by changing your speed, right? Slowing down from 50 miles an hour to 30 miles an hour, that's accelerating, or by changing the direction of your velocity by taking a corner, or some combination of both.